Module 11, Part B, Test Solutions. So consider this cylinder. The shape of the cross section that is parallel to the base is well, if we cut through this cylinder right here parallel to the base, we would be cutting off the same shape as the base if it's running parallel. So that's going to be a circle. And the cross section that's going to be perpendicular to the base. So if we cut through the top of the cylinder this way, straight down, we would make a rectangle in that direction. If you slice a cone through the apex or the tip perpendicular to the base, the shape of the cross section is what? So we're going to chop through straight down perpendicular to the base, and again we're just cutting off a 2D shape, and that would be in the shape of a triangle. So in this case we're cutting perpendicular to the base on this pyramid, but we're not cutting through the tip, we're cutting over here. So picture a block of cheese or something. If you cut through that, the shape you're going to cut off is going to be a trapezoid in that case. If you rotate this triangle around the y-axis, what is formed? Always something circular. We would end up with a cone. If you rotate this shape in this direction around the y-axis, it's going to fill in and it would make a sphere. In this case, if you rotate this rectangle, it's not touching the axis, so it leaves some type of separation. So you end up basically, I can't really draw this one, but you end up with a cylinder that has a hole in it. So it's kind of like a roll of paper towels or something. So this would be a hollow cylinder. All right, if you want to find population density, this is literally how you set it up. People, the number of people per, that means we're dividing, square mile, so it's the amount of people divided by the amount of space they have to move around in. Density is, in this case, is kind of an illustration of how crowded it is, how compact those people are. So in Madrid, we have 3 million, so we want to do people, 165,000 divided by space, and they have 234 miles in which to run around. So 3,165,000 divided by 234 square miles, and the population density there is about 13,526 people. 13,526 people per square mile. Okay, you find an old coin. Its mass is 57.9 grams and its volume is 3 cubic centimeters. Use the table of densities to determine what type of solid the coin is made of. So remember that density is equal to mass divided by volume. So our mass is 57.9 grams and the volume is 3 cubic centimeters. 57.9 divided by 3, we get about 19.3 grams per cubic centimeter, and that's of course closest to gold. We have a block of wood and we happen to know its density and its volume, the amount of space it takes up. We want to come up with the mass. So again, density equals mass over volume. The density is 0.6 grams per cubic centimeter. We do not know the mass, but we know that the volume is 1.2 cubic centimeters. So in order to solve for mass, we're just going to want to multiply both sides by the 1.2 to solve for m. So 1.2 times 0.6, and we get 72 hundredths of a gram. Okay, so now we're moving on to similar figures, similar solids, similar figures. So the ratio of two side lengths, sides are one-dimensional, is 3:7. Find the ratio of their volumes. Volumes is 3-dimensional. So if the linear ratio is 3/7, we're going to need to raise that to the third power since we're looking for the volume ratio. 3 times 3 times 3 is 27. 7 times 7 times 7 is 343. So what do you know about spheres? Spheres and circles are always similar. So these are a different size, but they're the same shape. So they're not congruent. We can only say that they are similar. If these cylinders are solid, find the volume of each solid to the nearest tenth. Well, if they're similar, they're not drawn to scale. If this height is half of that height, then this radius must be half of that one. And volume, find the volume for the cylinder is pi times our radius squared times the height. Pi times the radius squared times the height. Okay, so the volume here, pi times 2.5 squared times 5 is about 2.51. I don't see any of those choices there. Oh, I did that backward, didn't I? Okay, and I didn't type that in correctly. Here we go, let's try that again. It's pi times 2.5 squared times 5. There you go. About 98 and 2/10. So it looks like this one. Let's just double check. So for the larger cylinder, we have pi times 5 squared times 10. And we end up with about 785 and 4/10. So that's going to be choice C. Solid A is similar to B. The volume of A is 216. The volume of B is 125. Find the ratio of their surface areas. Okay, so we've been given A to B. When we set this up, the volume of A is 216. The volume of B is 125. This is our 3D ratio. We need our one-dimensional or our linear ratio. So what I'm going to end up doing is taking the cubed root. So the cubed root of 216, it's going to be 6, but you need to figure out for sure how that works on whatever calculator you're using if you don't know that off the top of your head. But that's 6, and the cubed root of 125, 5 times 5 times 5 gives us 125. So we end up with 6/5 for our linear ratio, but we want the ratio of their areas, so that's going to be 2D, so we will end up squaring both of these. So that will be 36 to 25, and there we go. All right, once again, A is similar to B, and the ratio of their surface areas is 36 to 25. Well, notice that's just what we had over here, and we know the volume of one solid and we're trying to find the volume of the other. So we're going to need their volume ratios. I might as well just grab it from this other problem. The volume ratios, if their surface areas are 36 to 25, then remember their volumes were 216 to 125. And this still is A to B. So A over B. If the volume of A is 252, so that's going to go there, what is the volume of B? And we'll take cross products to solve this. So we have 216 times X is equal to 125 times 252, 31,500. And then we'll have to divide both sides by the 216. And we get about 145.8 cubic centimeters. And then our final question is on Cavalieri's principle. So we have two shapes here. This one is a right rectangular prism. This one is an oblique triangular prism. The question is, are they going to have the same volume? Well, Cavalieri's principle, we want to check two things. Number one, are the heights the same? Yes. Number two, is the area of any cross section when you're at the same height on the figure always going to be equal? Well, the cross section here is a rectangle, 6 by 4. So this has an area of 24 square inches, base times height. And the cross section here, a little difficult to see, but that is a right angle on that triangle. So the legs are the base and the height. So the area is 1/2 times the base times the height. Half of 8 is 4. 4 times 6 is 24 square inches. And notice that the shape stays the same all the way up the prism. So the areas are equal at any given point along that height, and the heights are equal. So yes, the heights of both prisms are the same and they have the same cross-sectional area. Therefore, they have the same volume.